This is the second video segment that I'm going to be making on usage of dynamics in Catia v5. The first one was an overview of what dynamics is and a little bit about how dynamics is done in Catia, but not any specific example. Now, what I would like to do is to show you how to model this problem in Catia. So we have two masses. This is a 2 degree of freedom system, two masses, and connected with some support via these springs. And the values are given here. Now, later on, we're going to put a load here and find out what the response of the structure is due to this load. However, if we ignore the load momentarily, this structure has two natural frequencies because there's 2 degrees of freedom, and these natural frequencies are given as with these expressions, both in radians per second and hertz. This particular example I've taken from a textbook in vibrations by Ra, which is down here. The reference is down here. Now I want to say a few words about these type of problems, doing these type of problems. These are lumped mass spring, possibly damper systems. I don't have any damper here though. Catia is not a very user-friendly package for doing these kind of problems. If you have a complicated geometry and you want to know what is the response due to a load and things like that, with complicated elements such as tetrahedral, shell element, beam element, it's a lot easier to do than this lumped parameter system. So, although in all likelihood, in a real life dynamics, you will not be dynamics problem will not be specifically asked to do these kind of problems, but it is important because many of our students take vibration courses, and in the vibrations courses these are primarily the stuff that we start with, and it is expected for them to be able to go and model these things in a code of their choice, and Catia happens to be ours here. Okay, now here's the situation. I'll show you how to do that in a second. And this is the load is actually given here. So for time less than 0.1 second, the load is a constant 25,000 Newton, and then it drops to 0 and it goes on. Now, if I apply a static load of 25,000 pounds, you can actually go ahead and calculate the amount of deflection. Deflection of load mass 1 is going to be 0.5 millimeter, and mass 2 is going to be 0.3. Okay, this is static. In other words, somehow this magic load was applied so slowly to 25,000, and these masses are going to move, and you get these numbers. Now, if the problem is dynamic, such as here, the way I want to solve it is dynamic. In other words, suddenly this load is applied, then it becomes a dynamic problem, and in Rao the solution is obtained. The displacement of the mass 1 as a function of time is here, and displacement and mass function of mass 2 is there. Okay, and these are, by the way, plotted here, so you can see that at the end of right before the load drops, the mass 1 has moved by about 0.37 millimeter. Okay, these are on millimeter, and the mass 2 has moved by about 0.17 millimeter. Okay, now this solution that I gave you in the previous transparency is not valid, obviously, for past motion of the masses after time 0.1, because after that there is no load and it becomes a free vibration problem, and you just have to get the initial condition at that instant, and then solved as an initial as a free vibration problem, 2 degree of freedom system. Okay, so let's go here. Here's my Catia. The unfortunate thing about the way this has to be done in Catia, at least as far as I know, maybe wrong, is although you don't have any solid geometry, you don't have any elements in the traditional sense, such as beam bar or beam shell and solid, if you tetrahedral, if you don't create a geometry with those things on it, you cannot model this problem as a long parameter system. So that needs to be done. It's not going to be used, but it has to be there, otherwise we can't do the rest of the problem. Okay, so here's what I'm going to do. First I'm going to make a dumb geometry, a box, okay, and mesh it. Okay, so here is, let's see now, I'll take this plane. I'm going to draw something on it. Let me put some dimension here so that I know exactly what these sizes are. So this is okay, almost one inch. Okay, fine. The actual size doesn't matter because you're not going to be using that anyways. And I know you're going to say, well, what the heck? If we're not going to be using it, why are we creating it? Actually, you know what? Let me move it to the other side so that they don't obscure my view. Here, I'll move it there. Exit. Okay, good. And then path. This thing is never going to be used, but it has to be there. It has to be meshed, and otherwise you can't proceed. All right. So let me actually put some material on this thing. Once again, it's totally irrelevant, except that if you don't have it, you don't put a material on it, you won't be able to proceed. Right there. Now I'm going to create 3 points. Now these 3 points are going to be these points, point 1, 2, and 3. Okay, so let's do that. Okay, so first one is going to be 0, 0, 0. This is where the mass 1 is going to be located. As a matter of fact, you know what? Let me move this thing further down the road so that I can see it better. So this is where mass 1 is going to be placed. Okay, another one. Let's make it 5, where mass 2 is going to be placed. I don't want to make this thing longer. These dimensions mean nothing because they don't participate in the calculation, because the spring does not have a length for all practical purposes as far as we're concerned. And let's make it a 14. Okay, these dimensions, as I said, mean nothing. Okay, but I separated them so that I can see what's going on. All right, so we're done. As far as the model is concerned, we're done. I want to point out to you that some packages have discrete spring elements that can be used, but Catia does not have those discrete spring elements. So we have to fool it or trick it so that it thinks that it's having this discrete element, spring element. Okay, so first of all, let's go to the generative structure analysis. Catia sees this part. It immediately meshes it. Okay, look right there. And since this is never used, we might as well make the biggest possible element that we can have. This is 0.08, so I'll make it, how about 2? Okay, don't worry about that. I'm going to hide it. Right click, mesh visualization, and let me hide this so that it doesn't distract us. Right there. See, this is the biggest possible element that I can have. Model this thing. All right, so let me deactivate this. Good. There are my my points that I create. Okay. Now you see, if I did not have this, and I would go to that generative structure analysis, I will not get any of this stuff because Catia won't do it. So let me create a connection. Here, this is connection. Component, first component, this point. Second component, that point. Eventually, this is going to become my spring element. Don't worry about handle point, there is none. Let's do another one. Let's do another one. Between this point and that point, say OK. So we have created 2 point-to-point connections. These two, okay. Now, I want to describe what is the I want to turn these into a spring element. So you don't see spring element by itself anywhere, but you see this guy under distance connection property. You see user defined distance connection property. You click on it, And you see, support. Let's start with this one. This is the first connection that I created. Because it's point-to-point, immediately it deactivates the start and end and just takes the middle point. And I want rigid, spring, rigid. Okay, and you click on this wrench, you can input the stiffness of that spring in the direction that you want. Now I believe that was my first one, which was 150 mega Newton. So I'm too lazy here. Let me make it like that. 150 mega Newton meter. I think it automatically converts it to yeah, it automatically converted to Newton per meter. You say OK and OK. Now let's do one for that guy. That guy is 75. Okay, so another user-defined distant connection property, and this is the one. As soon as you select this, it dims the start and end and just takes the middle one, and you click on it and you make this thing 0.75. 0.75. Say OK. And OK. All right. Now, I want to apply my restraints and the load. Remember, this is going to be my wall. This is going to be wall. And this is going to be where the load is applied. So let's actually clamp. The first thing we do is we clamp all the sides of this, because this is not going to participate in my calculation. And the only reason I'm doing it, because that's how the rotate Catia or the modified FEA program to be put in there. So this does nothing. It just sits there. What is required in order to do that lump system. Now, this end is clamped. Okay, so let's see that. Clamped. This is the wall. There we are. And these two, this is where the masses are going to be eventually put. I'm not going to worry about it right now. Eventually put, and they move only in the x direction. So we go user defined. Okay, user defined. They cannot move in any direction except x. Okay, so this is where you see this can only move in the x direction, and I can simultaneously use this one, but I will okay, I'll do that. That's fine. So these two can only move in the x direction. Very good. Now I want to put a load here, because remember in the earlier video segment I suggested that you always do static analysis so that you can identify any mistakes, because in this problem I showed you what happens if you assume that the load is static. I calculated these values and I came up with well, I want to compare Catia result with these. If these are not matching, obviously dynamic, anything that you do dynamic is going to be wrong too. So it's going to be a force, okay, at this point in the direction x. Direction x, so this is going to be 0. Direction x, I'm going to put 25,000. 25,000 Newton. Now my units are in pounds, so also automatically it's going to get converted. You know what? I'm going to change my units here. Tools, let's see now. Tools, options. So length, I'm going to make it millimeters. Length, I'm going to make it millimeters. And where is the, what did I change? Oh, the force. The force, I'm going to change it to newtons. Okay. Sure. Okay, so in fact, if you go to your load, you see that you see 25,000 newtons right now, right there. Okay, good. Not a big deal. So we're gonna first of all, let's save everything. File, save management, analysis, save as. Let me go on the desktop. I make a new folder. I'll say 2 degree of freedom system, 2DOF. Example from Bravo book. All the stuff is going to go in here. And then we're going to run it. Nothing fancy is going to happen. Because notice that this guy here doesn't go anywhere. And alright. So let's look at the deflection, displacement. Okay. We move this thing here. There. Now, I'm going to double click on this because you're not quite sure displacement of what, because there is no color here. I mean, these are discrete elements. There is no color in the usual sense. These mean nothing. So double click on it and it says, well, what is it that you want to plot? I want to plot not everything, but I want the connection 1. Remember, connection 1 mesh. This thing was the was for mass 1. You see this? This is 0.5 millimeter. 0.5 millimeter. Now you want to see the mass 2. So don't give me this. Give me the other one. You see? 0.33 millimeters and oops. 0.33 millimeters. So it is right. Good. And there's nothing else you can do here. Unfortunately, I looked everywhere to see whether I can. Well, let's worry about it later on. All right, so save everything. Now we're going to insert a frequency case. Okay. So it says that, all right, what about the restraint? Do you want the new restraints? The answer is no, I don't want new ones. I'm going to use the restraints from static, right here. Where's my static? So whatever I put in the static case, I'm going to use that. And say OK. All right. Now, I need to put masses here. There's a mass here, and there's a mass there. So look for masses, lumped masses right there. You click on it. This is the first one, right there. And the magnitude of it, let's go and find out what it was. It was 200,000. Okay. So this is yeah, M1. Okay, so that's going to be 200 e to the 3. I can use I could have used different units for mass, but that's okay. I think that's going to be in let me check that. Where are the masses here? We're doing a frequency case right there. The first one I put in there, 200,000 kilogram. And let's do another one. Where's the mass? Right there. And that's going to go right here. And it is, there's a 5 there, 250,000. Okay, good. Okay, save everything. Now, notice that when you do frequency analysis, there is no load because we're talking about free vibration. Now, if I run this thing, you'll see what happens. It's going to come back and complain. It's going to say, wait a minute. You're asking for the first 10 natural frequencies. This problem is a 2 degree of freedom system. It does not have 20 or 10 natural frequency. You say, okay, fine. So what you do, you double click on this frequency case and don't ask for the default 10, ask for 2 only. Okay, run it again. No more complaints. And let's look at our frequencies. For example, let's see now, we can plot the deformation. Double click on it. Okay, so under occurrence, it says you have 2 frequencies, 1.94 Hertz and 6.16 Hertz. And that agrees with these 2 values. So this is correct. Fine. You say, okay. All right. Now we want to do a transient dynamic problem, or a dynamic problem, where this load is specified. Okay, so first thing I need to do is to create an Excel file which represents this particular variation. So let me see for a second. I've already done that, so let me go ahead and it's right there, you can see that. So it's 2 columns. The first column is going to be X in seconds, that's going to be time, and this is going to be Y in Y, okay? And right now there is because here, just look at this for a second, because I applied the load of 25,000 already, and I'm going to be using that, so I can, these heights are non-dimensional, okay? So it's going to be that 25,000 that I applied to that endpoint times 1 and times 1, and then it's going to drop to 0. It is possible to make these things 25,000 and in the actual problem apply a 1 pound load, for example. But anyway, I'll leave it the way it is. This is already created for you. You can also do it in Notepad, but let me go here and see what happened right there. All right, so first thing I need to do is to import a modulation file. It's that Excel file. Let me see if I can find it here. I don't know, maybe it's closed, so I have to go get it. Oh, okay, right, it's right there. But then I have, of course, obviously I have to go insert transient dynamic response, right? I just did the frequency case. This is insert transient dynamic response. And I'm going to be using the frequencies that we already calculated. It's right here. Okay, right there. This is our reference. We're going to use these. And it's a load excitation. Okay. Good. Now notice that these are not dimmed anymore. So this is going to be frequency. It's not what we want. This is going to be time modulation. And we go and select that folder, that file that I created. I think it is, it was put in, right, oh, not there. I had it in a different folder. Let me see for a second. Oh, was it there? Oh yeah, right there. But Excel, I want the Excel files. No. Let me go ahead and find out where I put that thing. Okay, it is in your raw 2 degree of freedom, etc.